This is your presenter Asloob Mudassar, and I am presenting slide number 122 of the course on laser physics. Question is, if a laser in a single mode operation is operating at one frequency, it may tune to some other frequency in the gain profile of the laser with a different line width, and the process is called frequency pulling. Discuss frequency pulling and limit to monochromaticity. The answer is, consider a single mode laser operating with a cavity mode nu c having a line width delta nu c. Nu c is assumed to be different from the central frequency nu naught of the laser transition, which has a line width equal to delta nu naught. So let me show you these parameters in the diagram. The caption is spectral output of a single mode laser under frequency pulling effect. So this is you can see this solid broader curve is actually the laser gain profile curve. And the central frequency of the laser source will be nu naught. And there are many longitudinal present under this gain profile. So this is giving you actually the shape of a multi-mode laser. Or and this could be a homogeneously broadened or slightly inhomogeneous broadened. So here we are assuming that our laser is operating at a single mode nu c, and the width of that mode is delta nu c. This is the line width of this mode, delta nu c. So during the operation of the laser at a single frequency nu c, it could shift towards the frequency nu naught. And in doing so, it may be oscillating at some intermediate frequency, for example, nu L, with a line width delta nu L. So the output spectrum could be delta operating at a frequency nu L. So we want to actually discuss the shifting or the frequency pulling of the laser initially operating at nu C and then shifting to another frequency nu L, and the laser then operating at some frequency nu L, though it ultimately try to move towards the frequency nu naught. So this is what we shall discuss about all this gain profile. So you see that if this gain profile is operating at a single frequency nu naught, then of course the line shape of this gain profile under a single longitudinal mode operation will be similar to that of nu L, though it will have a height up to the value up to this one, and it will be slightly maybe more narrowed in comparison with the nu L. So this is what we are going to discuss about this gain profile. So during laser operation, the cavity mode nu C will be pulled towards the central frequency nu naught, and in doing so, it may acquire an intermediate value nu L lying between nu naught and nu C. We assume that nu L has an associated line width equal to delta nu L. The modes nu naught, nu L, nu C, and their corresponding line widths delta nu naught, delta nu L, and delta nu C are shown in figure 1. So you see that the line widths, these are the single longitudinal modes. If the laser is operating at a single longitudinal modes, the modes could be nu C, nu L, and nu naught. So since we are saying that laser is operating at a single mode, it means that at a time it will either be operating at a nu C, or will be operating at a frequency nu L, or will be operating at a frequency nu naught. And the corresponding line widths are delta nu C, delta nu L, and delta nu naught. And here you will see that the frequency nu C frequency is greater than nu L, and nu L is greater than nu naught. Or we can say that nu L frequency, which we shall be considering as our frequency at which the laser gives you an output, this frequency nu L will be is lower than the frequency nu C. Assuming that nu naught, nu c, delta nu naught, delta nu c, laser output power P, and the populations of the laser level N2 and the lower laser level N1 are known. So you see that we are considering, of course, the two laser levels are being considered. The upper laser level is labeled having a population inversion equal, having a population equal to N2, and the lower laser level having a population equal to N1. So you can consider these two levels as the levels in the quasi 3-level laser system, or as the two lasing level as the two levels as the two laser levels in a 4-level laser system. We want to find the expressions for nu L and delta nu L. And we are assuming the other parameters are known. And we want to express over new expressions for nu L and delta nu L in terms of these parameters. That is nu naught, nu C, delta nu naught, delta nu C, and the power and the output power of the laser beam, and of course the populations of the upper laser level N2 and lower laser level N1. Strictly valid for a homogeneous line or approximately valid for an inhomogeneous line. The frequency nu L under semi-classical approach is given by, as shown in equation number 1, that nu L will be equal to W naught times nu naught plus WC times nu C divided by nu naught plus WC, where nu naught and W, where nu naught and W, where W naught and WC are the weighting factors given by W naught is equal to 1 over delta nu naught and WC is equal to 1 over delta nu C. For a typical low power helium neon laser under Doppler broadening, delta nu is of the order of 1 gigahertz. For example, for a typical helium neon laser, it is 1.7 gigahertz. So we are talking about a lower laser level having Doppler broadening, and delta nu is equal to 1 gigahertz. Delta nu C for such a helium neon laser is 1 megahertz. So if you calculate WC from the factors WC defined by 1 over delta nu C and W naught 1 over delta nu naught, we can find out the relationship that WC is of the order of 10 to the power 3 times W naught. The treatment of this subject in greater detail will require quantum electrodynamics treatment of the subject. But you know that we are using a semi-classical theory, and we want to borrow some results from the quantum electrodynamics treatment as well. But we shall not prove that one because we are not following that treatment. The width delta nu L is set by the spontaneous emission noise, or more accurately by the 0-point fluctuations in the mode fields. So these are the quantum electrodynamics descriptions. The spectral broadening of the output mode is due to random phase fluctuations of the 0-point field, whereas the amplitude fluctuations in the mode are due to amplitude and phase fluctuations of the 0-point field. These concepts can only be explained with quantum electrodynamics treatment of the subject. It is now well established that the output power of a laser in a given mode is insensitive to the initial number of photons present in the cavity for initialization of the spontaneous emission process. The rate of increase in cavity photons due to spontaneous and the stimulated emission processes is given by. So for the spontaneous emission process, d phi over dt, that the rate of change in photon, is given by the term Va times capital B times n naught. And through the stimulated emission, we shall find that the decay of a photon, or the rate of change of a photon, is given by this expression for the stimulated emission, for the stimulated emission or the stimulated absorption case, or in general for the stimulated process case, the result is Va times B times n naught times phi naught. The equation number 2 and the equation number 3 that is the rate of change of a photon through spontaneous emission and through the stimulated emission are explained in the appendix. So let me take you to the appendix 1. This is the rate of change of a photon, that is d phi over dt is equal to Va times Be times phi times n naught minus Va times Ba times phi times n1 minus phi over tau c. This equation has been discussed in equation number 111.2 or in the slide number 111. I shall suggest that you can consult slide number 111 if you want to deeply understand these equations, where Va is the volume of the active medium, Be is the stimulated emission coefficient per photon per mode, and Ba is the stimulated absorption coefficient per photon per mode. N2 is the population of the upper laser level, N1 is the population of the lower laser level, and phi is the number of photons present in the cavity at any time t. And minus phi over tau c, here tau c is actually the lifetime of the photon in the cavity. So this terms which has been shown in green is actually the change in number of photons due to the stimulated emission process, because the first term is due to stimulated emission, the second term is due to stimulated absorption. And we have combined these two terms, and we have labeled these two terms as d phi over dt and with the subscript as st. And here capital V is related with the capital V, which is the volume of the active medium, is equal to L naught, the length of the active medium, divided by L, the length of this is L naught is the length of the cavity, and this small L is the length of the active medium rod or the active medium region, and Va is actually the volume of the active medium region, whereas capital V is the total volume of the resonator. So this d phi over dt due to stimulated emission is equal to the difference of these two terms, and we can take Be is equal to Ba, and we can set these two equal to capital B. So, and we can set N2 minus N1 is equal to N naught, which is the population inversion. So we can these two terms can be written simply as Va times B times N naught times phi. Here n naught can be set as n2 minus n1, and you can take the population of the lower laser level to be equal to 0 or nearly equal to 0, and you can say that n2 minus n1 is equal to n2 minus 0 and is equal to n naught. And even if you don't take the value of n1 exactly equal to 0, and you can take a small number there in the lower laser level, even then you can replace the population inversion to be equal to by the term n naught. And you see that this is the term d phi over dt due to the stimulated emission is equal to Va times B times n naught times phi naught. And this is what you see that I have explained in equation number, I have given that one in equation number 122.3. So this is what I have explained. Now I am going to explain this term, which is due to spontaneous emission. Again, I am considering the second term in the appendix taken from equation number 111.1. So you should also consult slide number 111.11. So here you have the rate of change of the upper population dN2 over dt with the time is equal to Rp pump rate minus Be times phi times N naught. These terms have been explained, plus Ba times phi times N1, and then minus N2 over tau. Here tau is the lifetime of the spontaneous emission process. So this the negative terms indicate that the population will decrease due to this term. So the spontaneous emission term will decrease the population of N2. And you see that there is another negative term over here. It means that the stimulated emission will decrease the population of N2, whereas the positive sign with the Va with the Va term indicates that the population of the N2 level will increase due to the stimulated absorption. Now this term shown in red is actually the d phi over dt term, That is the term that gives you the rate of change of a photon due to the spontaneous emission. So I have separated out this term, that is d phi over dt due to the spontaneous emission sp is equal to n2 over tau, and n2 can be replaced by n naught and over tau. And this tau, similarly, since we are equating be equal to ba, and under the stimulated and under the steady state condition, we can also take 1 over tau to be equal to va times b. So we have this spontaneous emission photons, that is the rate of change of photons due to stimulated emission is equal to Va times B times N naught. And this is what I have given in equation number 2 of this slide, that is d phi over dt due to the spontaneous emission is equal to Va times B times N naught, where the terms Va, B, N naught and phi naught have been defined in slide number 111 and the slide number 112, or the question number 111 or the question number 112. Phi naught ranges typically for in the range of 10 to the power 10 to 10 to the power 16, and thus the contribution of the spontaneous emission process can be neglected when the laser is in operation, because the stimulated, because the terms are due, because the contribution of the photons due in the cavity due to the stimulated emission process will be much higher in comparison with the spontaneous emission process, so we can neglect the spontaneous emission process under that condition. The electric field of the output beam when it is lasing at a frequency nu L is given by E of t is equal to E naught into sine of 2 pi nu L into t plus phi n of t. So nu L is the lasing frequency, that is the laser is operating at a single longitudinal mode having frequency nu L, and phi n of t is explained over here, that is phi naught of t incorporates 0-point field fluctuations. So we have added a term to 0-point phase fluctuations. This is the fluctuations in the number of photons, and this is due to 0-point field fluctuations. The change in phase has the form as given by, so delta phi of t, that is a change in phase in the value of Et, can be given by the square root of the average of phi n at time t minus phi n at time 0, as given in equation number 5. The spectral shape of the emitted light, which we say that the power spectrum of E of t has a full width at half maximum given by, so delta nu L is equal to n2 divided by n2 minus n1 multiplied by the terms that has a numerator of 2 pi h nu L multiplied by delta nu C, the square of delta nu C, divided by capital V, where capital P is the output power of the laser beam. This is known as the Shallow-Towns formula, and it gives the quantum limit to the laser line width. That is, the laser line width delta nu L cannot be narrowed further as given by the terms on the right hand side, because the terms on the right hand side will limit the value of the line width known as the quantum limit to the laser line width. Because in order to decrease the value of delta nu L further, you either need to increase the value of P, which is not possible under fixed parameter conditions or under the steady state conditions, because laser is operating under the steady state condition, the power is fixed. So delta nu L cannot be reduced by increasing the power of the laser beam. And you know that delta nu C is also fixed, and h nu L, which is the energy of the photons coming out from the laser, is also fixed, and the population of inversions at the steady state, so n2 divided by n2 minus n1 is also fixed. So you see that delta nu L, which is the line width of the laser operating at frequency nu L, is also fixed by the terms on the right hand side known as the quantum limit to the laser line width. Now we are going to talk about another coefficient alpha square to be present over here for a laser, for a laser, for example a semiconductor laser. This formula needs a factor much greater than 1 on the right hand side to hold for a semiconductor laser in which, for example, in a semiconductor laser, fluctuations in electron hole density due to spontaneous emission results in fluctuation in the refractive index of the laser medium, which results in fluctuation in the cavity length. So the optical path length changes in the cavity. And due to that one, the change or fluctuations in cavity length changes the mode frequency. That is, the mode frequency could be either nu C or nu L or any other frequency, and thus changes the oscillation frequency of the laser output beam. Thus, for a semiconductor laser, the equation number 122.6 can be added a factor alpha square can be multiplied by a factor alpha square on the right hand side of that term, which is reproduced over here. That is delta nu L is equal to alpha square times the rest of the terms are the same as from equation number 6, where alpha square is much greater than 1, known as the Henry factor. And this is given to hold for delta nu L to hold for a semiconductor laser. That's why we have included a term alpha nu square of alpha. Quantum noise is responsible for the finite line width delta nu L in a semiconductor laser where delta nu L is greater than or at least equal to 1 megahertz, and usually it is greater than 1 megahertz in a typical semiconductor laser. But for a low power gas laser, the line width delta nu L may range from few millihertz to 1 hertz, for example, due to 0 point field fluctuations. Okay, and this could be determined using equation number 6, and the upper limit for the semiconductor limit could be determined using equation number 7. In nu is equal to n times c over 2l. You know that this is the condition for a single mode longitudinal operation. So this nu is the single longitudinal mode operating in the laser having a cavity length equal to L, and n is an integer value, some integer value, and c is the velocity of light. So if you take n as a constant, the relationship can be used to write this equation that delta L can be written equal to minus delta nu C divided by nu C multiplied by L. For that one, you need, for example, if you want to write down this expression, you need to calculate d nu over dl. So if you calculate du nu over dl, that is take the derivative of L over L square, which becomes a minus 1 over L square, and then reintroduce this factor again, you will find out that delta, and then replace delta d nu can be replaced by delta nu and dl du, because we are writing d nu over dl. This dl can be represented by delta L, and d nu can be represented by delta nu C, and the rest of the quantities can be obtained by reintroducing this equation in the derivative that I have just mentioned. So we can write delta L is equal to minus delta nu C over nu C multiplied by L. So if you increase the value of delta L, that is the length of the cavity changes by positively, that is the increases by delta L, then the delta nu C will be reduced. That is the delta nu will shift. You know that this negative sign indicates that is the width of the laser will be reduced. That is the line width of the laser will be shifted. So I am going to explain this equation, that is 122.8, more in a more elaborative way in appendix number 2. You see that this is the single mode equation. For a single mode, you can, if a laser is operating at a single mode, you can write this equation. And if the laser is operating at a frequency at a single longitudinal mode nu C, then of course the formula will be changed according to this one. That is, you need to have a length LC, and the corresponding mode is nu C. But if the length changes to some value, for example LL, then of course the corresponding mode will be nu L. From the figure, you can see that nu c is greater than nu L. So correspondingly, if nu c is greater than nu L, then of course correspondingly in the, comparing the denominator, we can see that LL is greater than LC, as evident from the above two relationships. So let us define delta nu as the change or the shift in frequency is nu c minus nu L. It is great. It is a positive quantity. We have taken it as a positive quantity, and delta L is equal to LL minus LC is greater than 0. We have also taken as a positive quantity. So in our definition, we have defined delta nu and delta nu L to be positive quantities. So you can calculate delta nu, which is equal to nu c minus nu L. You can put the value of nu c and nu L from the above these two expressions. So you have nu c and you have nu L. You can substitute these values in the expressions. For example, over here, you can take this factor n times c divided by 2 as a common factor, and you can have these values, that is 1 over LC minus 1 over LL. You can take the numerator, you can take the LCM of this term, and you have LL minus LC over LC into LL. And you can write this LL minus LC can be written as delta L, as we have defined over here. And you can write LL over here, and this LC can be written as n times C over 2 LC, and this term in red can be replaced by nu C, and then you have delta nu is equal to nu C times delta L over capital LL. So you can solve this equation for the value of nu L. So nu L will be equal to nu C minus nu C times delta L over capital L. So you can take nu c common as a common factor. Then we have in the parenthesis 1 minus delta L over capital L. And you see that this term, which is nu L from the figure, it is evident that nu L is less than delta nu c. You can see this figure again, that the value of nu L is less than the value of nu c, because it is lying to the left of nu c, and the frequencies is increasing towards the right. So you see that from here you can see that the shift in frequency to the lower value will be due to this value. When the change in the length of the laser cavity will increase, then of course you will shift towards a smaller value of smaller value of lasing frequency. So if the laser frequency, for example, is operating at some time t at a single mode nu c, and if its cavity length changes, that is increases by a length delta L, then the laser will shift to its lower frequency nu L, given by this expression. And similarly, we can say that so you see that we have defined this one, and ultimately, if delta nu is if delta L is for example, if the cavity L is reducing in size, that is, if delta L is negative, then of course the resulting frequency will shift, will be on the right hand side. Then nu L will be located on the right hand side of the new frequency. But if delta nu, that is the cavity length, is increasing, that is, if delta L is positive, it means that the laser frequency nu c will shift towards its lower frequency nu L. So I have explained the shift in frequencies. So this is called the shift frequency pulling, when the laser length, when the cavity of the laser length changes. So this is what I have explained this equation number 8 in more detailed as given in appendix. So this delta nu, so this is the expression that I have given in terms of delta L and delta nu c. So you can find the value of, you can take nu c on one side, you can take delta L on the other side, and you can shift, and you can control, and you can change the shift in frequency nu c due to the change in length of the cavity delta L. So this can be derived. So you see that this can be derived by taking the derivative of this equation also. A change in cavity length delta L will shift the cavity frequency nu c, and the oscillations will be set up at a new frequency nu L. Non-zero value of delta L is due to vibrations or due to thermal drifts. So you see that I have explained frequency pooling, and I have also explained the change in delta nu L, the change in the line width of the corresponding lasing frequencies. So this is the end of slide number 122.